Okay. Can y'all hear me? Is the audio okay? Just say something in chat. Anything. I don't really care. There's a bit of a delay on the stream, so I won't know for a little bit. Okay. Can y'all hear me? Is the audio okay? Just say something in chat. Anything. I don't really care. All right. Awesome. Appreciate you, Srithan. We're gonna start the stream at 6, so until then we'll just chill for a bit. So this thing is mostly gonna focus on like practice problems and stuff, instead of like a big content review. Just because, we're really close to the test. If you don't know, you don't know it. For everyone coming in right now, we're going to start at 6. We're just waiting here for that. T minus 6 minutes. We'll go ahead and start at 6. And tell your friends to hop on the stream, man. Got to get a higher turnout than this. Am I in high school? Nah, I'm a freshman. Well, I finished my freshman year at UT. And then for everyone coming in, we're gonna go ahead and start at 6 or 6 Central, wherever you are. Obviously, different time. I'm a neuroscience major, pre-med track. I'll probably get a minor in comp sci. How long is the stream going to be? It's probably going to last at least an hour. I'm not sure how much longer than that, to be honest. I did the chem stream. That one was like 2 hours, but there's a little bit more material in that course. So we're about 4 minutes away from getting started here. Last time we had audio problem, all types of FRQs. I mean, we're gonna go over like most of the topics. There's not gonna be like FRQs pulled straight from College Board. I made like this whole thing, so it's a little bit different. Doesn't follow the AP curriculum. That's rough. We're getting started in a couple minutes here for everyone that's just coming in. Physics is your biggest weakness. Hey, I mean, if you take it this year, right, it's going to be a lot better. Even if you fail the test, if you show up next year, you'll have like that background in it. It'll be a lot easier to take it your first time in college. Oh yeah, and by the way, if you guys are like, if someone's asking questions in chat, you guys can go ahead and answer if you know the answer. I mean, don't like spread misinformation, but if you know it. Yeah, spamming practice problems is the way to go for the most part, and then go back and check out stuff you didn't know. All right, we'll go ahead and get started in like a minute here. How good is the curve? There's not really like a curve, but I think it's like, I don't know, like a 70-ish. It will get you a 5, like 70%. Waves and optics. Um, Waves as in like harmonics, yeah, but not optics. That's physics too. Um, you're gonna have to ask your teacher honestly for the MCQ type questions. They usually don't release that stuff. There's like some bit of waves, but you're not gonna have to know like electromagnetic stuff. All right, it looks like we're at about 6 here. We'll just go ahead and get started. Um, all right. So let's just quickly go over the units and percentages, right? So we have kinematics. That's, that's like your average percent, I guess, like 12 to 18. Then we have dynamics. That's a bigger part. That's going to be like your free body diagrams and stuff. Um, and then you're going to move on to circular motion and gravitation. They really don't care about that stuff that much. They do care about torque though. And then energy is huge. You have to know kind of the basics about kinetic energy, potential energy, how they're going to transform into each other, stuff like that. Different types of potential energy, spring potential energy, gravitational, stuff like that. Then we've got momentum, and obviously that includes like impulses and a bunch of different types of problem setups. Then it moves on to simple harmonic motion. So this is the least important part of the test, 4 to 6%. If you don't get it, you'll be all right. And then last we have torque and rotational motion. So that's actually going to be another decent sized part of the test. Um, okay. The AP Physics test format. I You can just like look that up on the what's it called? You can just look it up on the College Board website. Yeah, someone already put it in chat. Yeah, you're gonna have a formula sheet. Ignore my mod, by the way. All right. So here's a big thing: the relevant math for the course. It's important that you're good at this stuff. So a big thing is the relationship between variables. So let's talk about what that means. It's easy, probably throughout your class, or relatively easy, to just plug numbers into a formula, right, and get your answer. But this doesn't necessarily translate to understanding how variables are related. So it's like if one variable changes, what happens to the other one? A lot of times they'll ask questions like, if the mass of something changes, how does that affect the momentum? And you got to be able to answer those. Why is it important? Obviously, they're going to ask a lot of these questions, usually as follow-ups. So they'll first be like, derive a formula, and then they'll be like, how would that affect this? You know what I mean? So, for example, how will gravity change if one mass is doubled? An understanding of these, it'll get you a lot of like quote unquote easy points. What do you need to understand? You should be able to understand and explain the effect one variable has on others in the equation, assuming everything else stays constant. Yeah, the stream will stay up. All right, let's try it. So if we have force equals mass times acceleration, how will force change if mass is doubled and acceleration is held constant? How will acceleration change if force is halved and mass is doubled? And then we've got some questions associated with the kinetic energy formula and the period for, I believe that's a pendulum. So you guys can go ahead and try these. Make sure you're trying the problems, because if you're not working through these, you're missing out on a lot. It's important. It's easy to convince yourself that you know how to do it, but you should be working through these if you can. Sorry, when I'm looking over, I'm just adjusting the TikTok stream. All right, so we're going to go ahead and show the answers for these. So with the first one, if mass is doubled and acceleration is held constant, the force is going to double, right? It's just a direct relationship. How will acceleration change if force is halved and mass is doubled? The acceleration will be quartered. Uh, so then with the kinetic energy one, and by the way, just put in chat if you need me to explain these. How will kinetic energy change if mass is held constant and velocity is doubled? So the velocity is squared, right? So if we double the velocity, the kinetic energy is going to quadruple. Um, and then if we hold velocity, wait, how will velocity change if kinetic energy is held constant and mass is doubled? In this case, velocity is on the same side as mass. So if mass increases by a factor of 2, velocity squared has to decrease by a factor of 2, which means velocity has to decrease by a factor of root 2. Um, okay, and then how will t change, t being the period, if L is quadrupled? So L is square rooted, right? So t is going to be doubled. And yeah, the last stream was a bit longer because that was my first stream, so I was doing funky things. I didn't realize how long the delay was between like me and chat, so I would wait until people would say they're done with something, and that would just be way too long. Uh, it's going to be a. Can you explain the second part of the kinetic energy one? So the kinetic energy one, the mass is doubled, right? So then the velocity squared has to be halved, and for that to happen, you have to divide velocity by square root 2. Okay, so then using trig, right? You're going to have to use this usually to find components of force. So in kinematics, you might need it, and then setting up problems in other units, drawing two-dimensional forces, and then also using the torque formula, because we know it's, what is it, force distance sine theta. So you're going to need trig for a lot of this stuff. Okay, so again, apologies if you already know this, but it's important enough that I'm going to go over it. Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent. Inverse sine, inverse cosine, inverse tangent. Okay, so go ahead and try these. Split this force on the left into its x and y components, and then on the right, find the y component and theta. So go ahead and try those. Again, we're starting off pretty easy. It'll get harder as we go. I'll move on to the more like conceptual questions. I have some of those in here. And for everyone just showing up, we haven't done a ton. We just went over some like basic math that you'll need on the test. And we're still going over that, so we haven't actually got to the physics content yet. That'll come up soon, in like, I don't know, 5 minutes max. Not even. Okay, and then for this one, we have sine 60 equals opposite over hypotenuse, right? Opposite being y. So then we can just solve for y. If you don't know any algebra with pertaining to these problems, you got to just review that on your own. You're going to lose a lot of points if you can't do the like algebra 1 type stuff. Same thing with the bottom one, except we're using cosine because adjacent over hypotenuse, and we're going to get 10 newtons. So let's look at this next one. We have inverse cosine with adjacent over hypotenuse, and that's going to get us theta. And remember to keep your calculator in the right mode, radians or degrees, and we'll go over how to convert between the two later, but I doubt you'll need to do that. Last y component is 30 meters. Just use the Pythagorean theorem. Don't overcomplicate these with trig if you don't have to. All right, so let's quickly go over the inclined plane because this is, yeah, remember to change your calculator to degrees. But we're going to go over the inclined plane setup because this tends to stump a lot of people. A lot of people lose points on this. So if we have a block on an inclined plane, right, it can move in these directions, these kind of slanted directions. And it cannot move, right, perpendicular to the plane. So what we're going to do, we're going to take gravity and we're going to split it into components. We're going to split it into the perpendicular and parallel components to the plane, right? And so what I did there, all I did, I just moved the red arrow over. Okay. So then the angle right here in this kind of green corner is the same as this white angle, just because of like parallel lines. That means that these angles are also the same because they're both right triangles. And so now if we look at this, we have a triangle that we can use to find components. So sine theta, right, is going to be our opposite over hypotenuse. That's going to be our like quote unquote sliding force, our like kind of cyan arrow, turquoise arrow. That's the one that's going to cause it to move. And then we're going to have our friction force, which is the one that's going to stop it from moving, which is going to come from the other component, the red component. So this is how we calculate both of these. Yeah, sometimes you won't have to break the components, but if you do, you got to use trig. So then we're going to get it into this component, and from that we can do the math for the other stuff. Okay, so I'm going to have this section at the end of every, I guess, section. If you learn nothing else, understand that variables in an equation are related to each other. If one changes, another will have to change in order to balance it out. Trig functions are useful in kinematics and diagrams, and SOHCAHTOA is your friend. Okay. If anyone has any questions on that section, just go ahead and put it in chat. Is there a break between the two parts? Yeah, I think it's like a, what, 5-10 minute break, something like that? I believe so. Because there's like a bathroom break and stuff. Yeah, don't break it up unless they tell you to. It's just gonna make it more complicated. But if you have to, like in a lot of kinematics problems, you got to break it up. Okay. Position, velocity, and acceleration. This is a big part of kinematics. Um, so let's talk about their relationships. Velocity is the change in position over change in time. Acceleration is the change in velocity over change in time, right? So graphical representation. So this is important. You might have questions about this on like the FRQ or on multiple choice. They'll be like, find the velocity based on this position graph. Is the Princeton practice good? I have no idea. I've never done it. Actually, I did it for physics too. It was pretty good. So is the horizontal always no. Cosine just means adjacent over hypotenuse. So like on the inclined plane, we saw they kind of flipped. The cosine ended up vertical. So just remember SOHCAHTOA. Don't try to say sine is vertical cosine is horizontal. It's generally that way, but it's not always. How many slides are there? I think there's like 50. Okay, so with graphical representation, velocity is the slope, right, of a position time graph. Acceleration is the slope of a velocity time graph. Position is the area under the line in a velocity versus time graph, and velocity is the area under the line in an acceleration versus time graph. And yeah, if you want to memorize the what's it called, inclined plane setup, that's fine. Like Ahmed is saying. Um, Scalar versus vector quantities. Scalar values have value but no direction. So distance, speed, temperature, right? So if we say like he went 10 miles, that's going to be a scalar. It's a vector if we said he went 10 miles east. Okay, so displacement, velocity, and force are going to be vector quantities. Okay, one-dimensional kinematics. Yeah, it's recorded. It'll stay up. One-dimensional kinematics, you're going to list out all your known values. You're going to find what you're looking for, and then you're going to find a formula that has all of the above. And if there's not a formula, you're going to have to solve for something to be able to use one of the formulas. So use that value to find a new equation that does what you want. If there's no acceleration, no net force, you probably don't need a kinematic equation. You can just use velocity equals distance over time. So that's usually going to be what you're going to use in the x components of kinematics, just because there's generally not acceleration in like a free falling situation. All right, and then with two-dimensional kinematics, um, I don't know any formulas you need to know but aren't at the reference sheet. If there are, you're just going to have to derive them based on what they tell you. How to start the problems, and we'll go over some formula derivation. List out all your known values, list what you're looking for. So it's similar to the first one. But then time is what links the x and y components. So time is especially important in 2D kinematics. So putting together x and y portions, only time is the same. Yeah, I'm going over every unit. Okay, so speed is just a value. So I can say he's going like 8 meters per second, and velocity is saying which direction he's going as well. So it's like he's going 8 meters per second to the left, that's velocity. So if you move to the left, usually we consider that negative. So we'll say like he's moving at negative 8 meters per second, but the speed of that is just going to be 8 because we don't care about direction. Hope that makes sense. Um, and remember, if you know the answer to like someone's question, you can go ahead and answer it. Using the givens and to calculate time, then use time to find what's missing. That's usually the process. So unless otherwise stated, there's no horizontal acceleration, and that's when you're going to use velocity equals distance over time. And gravity is generally the acceleration for the vertical part. Sometimes they'll like switch it up, say it's on a different planet or something, but same general principles hold. All right, so go ahead and try this problem. Uh, just letters, right? You're not going to see a bunch of numbers on the FRQs usually. It's going to be mostly conceptual to see if you know what you're talking about. So go ahead and try this, and then we'll go over it in a little bit. Anyone just coming in, we're still on just Unit 1. Can I move my webcam? Which way do you want it? Oh, shoot. There, I'll move it back after. All right, it should be good now. I'll move it back after this. All right, we're gonna start going over it now. So first, you got to figure out the all of your knowns. So we're gonna write out our initial y velocity, which is 0. Our final y velocity, we don't care about it. Our acceleration is 9.8, or you can just use g, depending on, whatever. Y minus y0 is h, right? So if we're looking at our change, right, in distance, it's gonna be h, because that's the height. And we're looking for time, right? And so with our horizontal component, our initial and final velocities are both just v, because this is not going to change. Acceleration is 0. We're looking for x minus x0, and we're going to get time from the vertical part. So we're going to start with this equation, right? Then we're going to move over y0. So now we can find y minus y0 equals h, right? So we're going to end up subbing that in. We know vy0 is 0. T is what we're looking for, so we're just going to leave it as t. I changed 9.8 to g here. I think that's just I meant to put g originally. Okay, and then we just kept t the same. So we can just solve for t here, and we're going to get the square root of 2h over g is equal to t. Okay, and now that we have that, we're just going to plug into v equals d over t because there's no acceleration for that part. And d is x, which is the value we're looking for. So x divided by the square root of 2h over g. Oh, shoot. Sorry. Okay. Okay. So then we have velocity equals x over root 2h over g. Um, velocity times the square root of 2h over g is going to be equal to x. Okay, so that's how you're going to find the distance here. If you have any questions, just go ahead and put it in chat. Okay, so now we're going to move up to some follow-up questions. Go ahead and attempt these. So if initial velocity was doubled, how much further would the ball go before hitting the ground? If the table was halved, how much less distance would the ball travel before it hit the ground? And then how would table height have to change for the distance the ball traveled to triple? Where do you get the y and y0? So y is just like kind of y minus y0. All that means is just the change in y. So I don't like the way they put it in their formula sheet, so I just kind of combine them into y minus y0. It's just going to be the distance traveled. Technically, it would be negative here, but if you just keep everything positive, things usually work out. With kinematics, not like with everything. All right, so this is going to be those variable relationships we were talking about earlier. So if the velocity was doubled, it's going to go twice as far. So the reason for that is if we look at this equation, we're trying to see how x would change if v changed, right? So here, v and x have a direct relationship. As v increases, x will increase proportionally. So that's the reason it would go twice as far. If table height was halved, the distance would decrease by a factor of square root 2. And the reason for that, uh, velocity is just v. You don't get an actual number. But with this, the distance would decrease by a factor of root 2 because if h decreases by 2, it gets square rooted. It'll decrease by root 2. How would table height have to change for the distance the ball traveled to triple? So we want x to triple, right? Assuming velocity stays constant, we're going to have to multiply h by 9 because it's square rooted to get that change there. So let's go over when to use kinematics. If there's any sort of constant acceleration and you got to do calculations, you can either do kinematics or calculus, and you probably don't know calculus. If you have a net force and a mass of a system, so how long is it alive? It's probably going to last until, I don't know, another hour or so. If you have a net force and mass of a system, then you can see how the system is going to move. So you can either see the kinematics of like an object or a whole system. Either one is fine. Partial credit for short answers. Yeah, there's definitely partial credit for the FRQs. Kinematic equations also apply in rotation. They have the same formulas, but you just swap the variables. So instead of like velocity, you'll use angular velocity, which they use like omega for that. Acceleration swaps for angular acceleration, stuff like that. Okay, so then if you learn nothing else, list out all of your knowns. Don't get thrown off by letters, and try to find relationships between variables, because that's probably going to be what the follow-up questions are. Okay, so then part 3, we've got dynamics. So as we saw earlier, this is a big part of the test. It's a special word for free body diagrams, essentially. So let's talk about what they are. So free body diagrams are a representation of an object or a system and all of the forces that have an effect on it. Remember, nothing can exert a force on itself. They're important because they can make sense of a complex word problem, right? It's hard for us to just like visualize it from nothing, so it's important to kind of write it out. It's good for visualizing forces and figuring out what they're going to do. So objects with a constant velocity have a net force of 0, right? Because nothing is making it accelerate, I guess. So objects with a changing velocity have a net force of non-zero. I know that sounds obvious, but it's important. Okay, so how to draw free body diagrams. You're going to draw all of your forces. So remember, you got to include gravity, normal force, electrostatics, applied force, force of friction, and force of tension. Obviously, you won't have to put all of them every time, but those are all of like the usual ones in Physics 1. There's also like spring force, but you know, that's similar to force of tension or applied force. Check if it makes sense. So make sure your vector lengths are proportional. So stronger forces should have longer vectors, and shorter forces should have shorter ones. Um, Make sure the sum of the forces is in the correct or like a reasonable direction, right? So just like use your brain there. All right, let me make sure you can actually see this. Okay. Hopefully this time you can actually read the problem. Go ahead and try making a free body diagram for this scenario. We'll go over it in a sec. Who here is from Leander High School? I'm just curious. All right, we're going to start going over it here. Okay, so here's our block, I guess. You're just going to put that dot in the center. That's how you're going to start all your free body diagrams. All your forces are going to come out from the center from Florida. Yeah, I would assume most of you guys are from TikTok, right? in Texas. All right, so gravity, it's always going to go down. Then we have our applied force, which is pushing to the left. We have our electrostatic force pushing to the right. Florida and Texas. No other states, it looks like. Then we have our normal force, which is going to counteract. You haven't covered this unit? That's rough. Normal force is going to act opposite to gravity. And we have our force of friction needed to keep the block stationary, right? Okay. So if we're assuming that gravity is 10 meters per second squared, that's going to tell us what our force of gravity is, and that's also going to tell us what our normal force is. New York, right? So we know that force is mass times acceleration. Electrostatic force, I guess that's not in the curriculum anymore. Maybe, maybe it is. I don't know. Yeah, if you put mg, that's fine. Electrostatics is just like two positive things repelling each other. Just understand that positives repel each other, um, and negative and positive attract. Doesn't the role force of friction? So in this case, right, we're applying a force, but the force in the other direction is still stronger. So friction is just going to stop an object from moving. It doesn't care which way the applied force is. Yeah, so it means no net force. All right. So we got to use our formula. Force of friction is our static coefficient of friction times normal force. So in order to balance this out, we obviously need a 100 Newton force left. So we're going to use that. That's going to give us a static coefficient of 0.2. And if you get that, you're going to get all of the forces to balance out, right? And that's going to mean that it's not going to move. Or if it is moving, it'll move at a constant velocity. Okay, and then if the static coefficient is greater than 0.2, this is still going to work. It would still be fine. Like if you think about, I don't know, let's say asphalt has a high static coefficient of friction. It's not going to push stuff randomly, right? It just means that it'll take more energy to move. So even if the static coefficient is greater than 0.2, it's just not going to move. Okay, so friction. How did I get friction forces 100? So I just looked at the left and right forces, right? We've got a 200 to the left, 300 to the right. We need to balance those out, so we need a 100 to the left. Thank you for everyone answering in chat. Friction, when is it important? Generally, the AP test will be very explicit about when friction is involved or not involved. They will tell you. You're not going to have to just like think about it. What to know? For an object to move, it has to overcome the force of static friction. Even if friction is greater than the force trying to move it, the object won't move in the opposite direction or something stupid like that. Okay, so this one's a hard one. I'm not gonna lie. This one's difficult. But go ahead and try it. It's gonna draw on some of the stuff we talked about earlier. But you know, there's hard problems on the test. I think this is a little bit harder than what you'd see. But go ahead and try it. Yeah, friction can be a lowercase f. Sliding? I just write like sliding force. I don't know. I don't know if there's like a standard abbreviation. Oh man, sorry. Sorry. Whenever you guys say like move the webcam, there's like a delay. Sorry about that. Yeah, I don't know. It's really annoying. I wish it would just like be, I don't know, like 10 seconds or something. I don't know why YouTube wants me to be like a minute delayed. So you are going to be using that, yeah, but there's a lot more to it with the inclined plane because you have to think about the friction and all of that. How would you go about it? Which equation? So we're going to be going over that in a second here. All right. So first, we're going to start about what we're going to start with what force is acting on it, right? We have the gravity, which is mg, and we're going to split it into our components like we talked about earlier. All I did there was just move the perpendicular vector to the right. Okay. Um, this is how we're going to calculate our perpendicular force. So the block cannot move in this direction, right? So we need something to cancel it, and that's going to be our normal force. All right. And now if we're looking for this force, this sliding force, we're going to use sine. I hope everyone can see this. It might be cutting off a little bit. Okay. Um, so then with this, um, we have the sliding force is going to move parallel with the plane, and so this can only be counteracted by friction. So our sliding force is going to be mg cosine, wait, what? Sliding force. I think that was meant to say sine. Yeah, it was meant to say sine. I don't know why I put cosine. Um, okay. So then our force of friction, right? It's going to be our normal force times mu. So our force of friction is going to be our normal force, which is mg cosine theta times mu. Force of friction, right? Just multiply them out. Uh, so then we're going to move on here. Let me drag my window up a little. Okay. So we have our mg cosine theta normal force, mg cosine theta gravity, right? And then we have our sliding force, which is mg sine theta, and our friction force, which is mu mg cosine theta, right? So what I did there, I just canceled these two. They're going in opposite directions. So now we have this going in opposite directions. So our net force is equal to mass times acceleration. Mg sine theta minus mu mg cosine theta is equal to mass acceleration. Right, so then this is going to be our acceleration, and we're just going to cancel our masses. So this is a bit of a rough problem. Usually it's not going to be this difficult, but this would be the process. Can you explain why you use cosine instead of sine because they're vertical components? So I used cosine uh, because it was adjacent over hypotenuse. It doesn't have to do with vertical or not. That used to trip me up back when I took it. Yeah, because remember there was a force applied. Oh, sorry. This is the acceleration without the force. So you'd have to overcome this, is what I meant. Yeah, sorry, I meant without the force applied. I don't know why I had that there originally. Okay, so then for like the main takeaways here, free body diagrams are generally easy points. Um, don't get thrown off by letters. They're gonna be without. Yeah, I don't know. I just like I put that in there. I think I meant to take it out. Don't get thrown off by letters, and then the free body diagram will help you visualize the net force. Okay, so then circular motion and gravitation. This stuff isn't super hard, and but sad part is it's not a big part of the test. Quick review of rotation math. So we've got degrees versus radians. Both degrees and radians measure the same thing. Degrees go from 0 to 360, radians go from 0 to 2 pi. When are they important? If a problem focuses on rotation, radians will probably be used. Otherwise, degrees, like in kinematics. Um, General tips, make sure your calculator's on the correct mode. That's an easy way to lose points if you don't switch it. Conversion from radians to degrees, you just multiply by 180 over pi. Conversions from degrees to radians can be done by multiplying by pi over 180. Okay, so relevant equations here, force equals mass times gravity when you're dealing with gravity. Gravity equals g m1 m2 divided by r squared, and then potential energy equals mgh. And so what to know? The force of gravity is directly proportional to both of the masses involved. Um, the force of gravity has an inverse square relationship, that's important, with the distance between the objects. And the general tips here, the formulas aren't hard to use. Uh, for that reason, they're just going to be like asking conceptual questions. It's important to understand the relationships between variables because that's usually what we're going to be at. They're going to be asking. Okay, so there's two masses, A and B. They're x meters apart and they exert a gravitational force of F on each other. Derive a formula for G um, using A, B, and X and any necessary constants. I think that's meant to say F, the force, the force between them. Okay, right, so we can just calculate it like this. So here it's just taking the formula and literally just plugging in what we were told, right? So m1 is A, m2 is B, r squared becomes x squared. Okay. So then how would the gravitational force change if the mass of B was quadrupled and the mass of A was halved? So remember, you got to use the formula that we just made and think about this one. So there's a way to like actually mathematically do it, or you can just kind of think about what's happening, and that's going to usually work out better. Okay, so here's the math for it. Um, if one mass was quadrupled, one was halved, then it's going to be doubled. You can do all this math for it, but it's way easier just to think one is quadrupled, one's halved. It's going to be doubled. Um, Ooh, didn't add a transition on that one. Well, here's the work for it. How would the distance between the masses have to change to make the gravitational force 4 times weaker? So remember, it's an inverse square relationship. If you double x here, right, then what we need to do, or what we're going to end up doing, is making the gravitational force 4 times weaker. And here's all the math for it, but again, it's way easier just to think about it like conceptually. Um, Doing this sucks. Okay, so Coulomb's law, I guess you guys were saying you don't have to know about it. Um, I guess they pulled it out of the curriculum. But it's very similar to gravitational law. Instead of G, you use C, and instead of M1, M2, you use Q1, Q2, and those are just meaning charges. And radius is still radius. It's basically the same thing. So, if you learn nothing else, understand the relationship between variables. That's another big important part here. And then know that Coulomb's law and gravitational force formula have similar properties. Okay, so we're going to move on to energy and harmonics. This is like the smallest part of the test. No, not energy, harmonics is. That's why I just grouped it in with energy. All right, so big ideas, conservation of energy. Energy can't be created or destroyed. I mean, I'm sure you guys know this, but it can change forms. Uh, Usually we won't be focusing on the specific types of potential energy, but you just got to know that that and potential can be interconverted. So with their relationships, don't worry about more than two planet systems usually. If there are, it's not they're not all multiplied. Just think of them all individually. Um okay, so their relationship, there's usually going to be some energy associated with the system, and this will be conserved unless there's friction. Then we're losing energy. But otherwise, potential energy and kinetic energy are going to make up all of it. Um K is just a constant there. It's not like anything specific. We're just trying to figure out how X changes. So we just used K as a variable. It didn't have anything to do with springs. So with that one, it was just way easier to think about it without all that math. So you could just think about it conceptually. If you want to quarter the gravitational force, then we would have to double the distance instead of doing all that math from earlier. Okay, so then with graphs, you should be able to interconvert between situation descriptions and graphical representations. And then don't be intimidated by it. Okay, relevant equations, right? These are stuff we've already seen. Um, Another one, potential energy is negative gravity times m1, m2 over r. Not super important. You might see it a couple times. Um, I don't know what you're asking. In terms of logistics, when to use which, right? So the first one is moving objects, rotating objects, then objects that change height to do work, objects that exert a gravitational force on each other, and springs. And so a good way to think about potential energy is like how happy something is, I guess. The lower the value, the happier it is, right? We know that if something is on the ground, it's got no gravitational potential energy. It's in its like resting state. It's like happy. If it's kind of in the sky, it's gonna fall. It doesn't like being where it is. Okay, so describing energy qualitatively is important. This will get you points on the FRQ. Instead of saying mass A is moving at 60 miles per hour and mass B is moving at 30 miles per hour, you would just say mass A is moving faster than mass B. It's just a way of describing things at a higher level to show understanding. Um, okay, qualitative understanding of situations are extremely important. So this block has more gravitational potential energy. This one has less. You know, It's not that this is a challenging concept, but it's just you got to be able to put them into words. Yeah, what Sreethan said. The happy thing with PE again. Okay, so if something has high potential energy, it's going to want to move to somewhere where it can have lower potential energy. It's not happy when it has high potential energy. When things have low potential energy, they're happy. They're not going to want to move. That's kind of the gist of it. It's happy where it is if it has low potential energy. Okay, so now imagine the block is falling from an initial position where it was at rest, and then picture it again before it hits the ground. Um, the block has more gravitational potential energy, but no kinetic energy, right? Now the block has less gravitational potential energy and more kinetic energy, but the total energy is not going to change, unless we're talking about like friction and stuff. Okay, but yeah, same thing here, same total energy. All right, so if we're describing energy qualitatively, let's talk about this graph. If we have a ball bouncing that hits the ground every 10 seconds, we'll create a graph of potential energy versus time, kinetic energy versus time, and total energy versus time with no units for anything except for time, because we're just doing this qualitatively. Let's say the ball is in the act of bouncing at time equals 0. So on this left side, it's in the act of bouncing, time equals 0. Okay. Um, so at the bottom, right, if we're looking at this first row across, our kinetic energy is at its maximum. It's not going to be moving any faster than when it's right about to collide. It's got no potential energy, at least no gravitational potential energy. You're not going to have to worry about like chemical potential energy. Um, all right, so let's look at the next row. Now it's in the middle of its bounce, right? It's going to have a medium amount of kinetic energy and a medium amount of kinetic energy or potential energy, right? And then in 5 seconds, it reaches its peak. It's going to have no kinetic energy at this point, and it's going to have maxed potential energy. And then this is going to repeat on the way down uh, as we see the kinetic energy increase as it falls and its potential energy decreasing, right? So let's go ahead and graph this, right? So I just moved the table we had to the left. Um, if we look at the wave, right, I just put the points uh, like at high or low. There's no actual values here. So we have at time 0, the first one is our kinetic one. So we can see it goes down before coming back up. And then potential energy is flipped, right? It's going to go the opposite way. But if we were to add the two graphs, we're going to have conservation of energy here. It's always going to be the same. Um, yeah, if you have something where like things are losing height every time, it's not an ideal system anymore. You're talking about like something that's actually happening, and that's just generally not going to be asked about on the test. Everything's super ideal here. Notice how they go opposite to each other. When one goes up, the other goes down. The total, uh, the total energy remains the same, and then you can add them and you get a straight line because the total energy won't change. Okay, so let's quickly talk about harmonics, banking off of that. Yeah, this is the only live stream I'll be doing for physics, I guess until next year. Um, so the shape of our energy diagram, right? Plotting energy versus time gave us a wave. This happens with springs and pendulums too. It's oscillatory motion. I'm not going to go into modeling it with like a trig function. Oh wait, what happened? But it can be modeled with sine or cosine. So amplitude of a wave is from the middle to the top. And then our period. Yeah, I know you don't need to know this, but it just makes the period stuff make more sense. I think, at least. So we have crest at the top, trough at the bottom. The period is going to be from bottom to bottom or top to top. Uh, relevant equations. We've got F equals negative kx. Uh, potential energy, right? Some of this is the same. And then you have to know that frequency equals 1 over period. Yeah, you don't got to know trough and crest, but it just, I don't know, it helps you understand if you have the whole picture. Um, K is the spring constant this time, yes. So then we have period formulas for springs and pendulums, and then we've got the velocity wavelength equation. Okay, so more stuff about harmonics. The period of a wave. From a graph, the period of a wave can be represented as crest to crest or trough to trough. There are other ways that are more complicated to find period. Energy of a wave, it's going to be proportional to its amplitude squared. You're not going to have to worry about that. That's not important. Energy is proportional to frequency for electromagnetic radiation. Again, not important. So let's talk about longitudinal. L in this case is the length of the pendulum. Longitudinal waves go in straight lines, right? So this is going to be like sound. Transverse waves are going to go like up and down. Wavelength is the length that the wave travels in one period. All right. So a wave with period p moves at velocity v. If the period doubled, how much would the wavelength of the wave have to increase to double velocity? So let's just go over this. We're going to use this equation, right? Velocity equals wavelength times frequency. Then we're going to switch it to 1 over period, right? So then velocity is wavelength over period. We're going to say we're doubling velocity, right? Doubling period. We're going to see how that affects wavelength. And we see that we had to quadruple the wavelength for this to work. Is the period always trough to trough? On a velocity versus time graph or acceleration versus time graph, it look different. Period usually won't be on an acceleration versus time graph. That's like other stuff entirely. Okay. So then if we have this, um, we're going to go over, this part is actually like on the test. So if we have a spring with a mass hanging, it oscillates at the frequency of f. How would the mass have to change to double the frequency? So this like pendulum stuff, it's springs and pendulums are still going to be on there. All right. So we have that period is 1 over frequency. We're going to plug that in. So doubling frequency means having the period. If you learn nothing else, understand that energy is never lost. It only changes form, be able to graph situations, and if you don't understand harmonics, it's fine. It's like 4 to 6% of the test. Okay, so momentum here, this is a pretty decent part of the test. So you always want to draw out these problems. It'll help you understand things a lot better. So momentum is going to be mass times velocity. Impulse is force times time, which is going to be the same units as mass times velocity. And there's elastic versus inelastic collisions. Elastic meaning that no kinetic energy is lost, inelastic meaning there is kinetic energy lost. So some main ideas, things are going to crash into each other, join, break apart, and more. If you draw out things, it'll help you. Yeah, the live stream will be saved. It'll stay up. Um, it's important to be able to draw out what's happening so you can do the right math. Draw out the befores and the afters. That's going to be important. So understanding systems. A system is going to conserve momentum, I guess unless it tells you it won't. be able to figure out what will move together. It would only not conserve it if there's friction. Um, Remember negatives, assign negatives to things moving left or down. A train, does this guy know what he's talking about? That's crazy. A train car moving at 15 meters per second to the right crashes into another car moving 5 meters per second to the right, and following the collision, they remain together. If the first car was twice as heavy as the second, how fast do the conjoined cars end up moving? Try to draw the before and after. This one's not super hard, but just go ahead and try it. Okay, so if we draw the before and after, right, we know that it's going from 2 meter, wait, no, a two mass thing going 20 meters per second, and then a lower mass thing. You got to see the Sixers play. Um, okay, and then they're going to join together, right? We're just going to set up the formula. We're just going to plug everything in. You're going to get 15 equals velocity. Yeah, definitely what Sreethan is saying. Practice problems are way more important than review. Uh, Now, what if we weren't given starting velocities? Create a formula for the final velocity of the combined cars. Assume starting masses are the same. The first car is twice as massive as the second, right? So try setting that up. No, you know what's crazy, dude? AP Physics did not give me physics credit. It gave me like physics lab, which is insane. I literally didn't get like I got one single hour from this class. I got a five, dude. I got a five and I got 1 hour off of it. I got also off physics two, I only got 1 hour. It was absurd. Elastic just means that you're conserving kinetic energy. That's all it means. That's the only difference. Right, so if we were to set this up, this is how it would go. You'd find your velocity is equal to that. What college do I go to? I go to UT Austin. But yeah, Shrithan is right. It does help a lot. Uh, it shows your problem solving skills. Um, yeah, I go to UT Austin. So for us, you only get physics credit off of physics C, which is really annoying because I just kind of wasted 2 years. Elastic is when kinetic energy is conserved. So just like energy, momentum's always conserved. Always draw it at situations, even on the multiple choice. They're not going to see it, but it's good to do. Okay, torque and rotational motion. We're almost done here. This is the last little bit. Okay, so what is torque, right? Torque can be thought of as a spinning force, right? Higher torque is going to be when the object will have a higher tendency to spin. Main ideas here. This is going to mean that perpendicular forces have higher torque, right? And that's just going to be in the formula with sine. Centripetal acceleration is going to be velocity squared over radius. Um, and then we have a different angular acceleration, which is going to be the sum of the torque divided by the inertia, rotational inertia. So it's very similar, right, to the force sum of forces over mass. So then we have um, L equals IW. So this is just angular momentum is inertia times angular velocity. So that's very similar to our MV for regular momentum. Relations to the non-rotational stuff. Mass is a tendency to resist change in motion. Inertia, in this case, is a tendency to resist change in rotation. Angular velocity versus linear velocity. Similar thing. It's just angular. It's going in a circle, right? Okay, so what angular stuff actually means. Um, Angular velocity versus linear velocity. We have radians per second versus meters per second. So a radius can be expressed as meters per radius, right? So angular velocity times radius is linear velocity. That's something that you guys might need on the test. All right. So a gear with 6-meter diameter has a linear velocity of 36 meters per second. What's the angular velocity? That's crazy. 5 hours a day for 2 weeks? You better be one of those guys who gets every single point. So here you got to find radius, right? It's half of diameter. Uh, it's going to be 3, right? Linear velocity is angular velocity times radius. And you can just calculate your angular velocity here. Okay, so here's a somewhat difficult problem. There's a pulley system with two masses. Mass 1 is twice the mass of mass 2. The pulley that M1 is attached to has a radius of r and rotates together with the larger pulley of a radius 4r, and that is attached to mass 2. Mass 1 is 10 meters above the ground, and mass 2 is 5. This guy's a freshman. Mass 2 is 5 meters above the ground. Um, use gravity with 10 meters per second squared. And inertia is going to be the sum of mass radius squared. What math are you in, Srithan? If you're in physics right now? Because we had sophomores taking it. We didn't have any freshmen. Pre-cal? Good God. Okay. So we're going to want to find the net torque on the pulleys, right? So this is the process for that. The difference is going to be the clockwise versus counterclockwise. It's not going to be like left versus right like in normal problems. With angular stuff, it's going to be clockwise, counterclockwise. So we're just going to use FD sine theta. Everything here is perpendicular, so sine theta is always going to be 1 because sine of 90 is 1. Um, so that's how you do this stuff. Okay, so assuming long enough ropes, which mass is going to hit the ground, right? Um, so what we're going to do here is we're going to calculate our rotational inertias. Yeah, I took it in junior year. Can I go over this question in depth? Okay. So this question is pretty similar to the God, which one was it? Let me see if I can find the one I kind of modeled it after. Um, 2021 maybe? 21 AP Physics FRQ. Yeah, so if you want like a good explanation of this one, you can go to 2021 FRQ number 5, and that one's pretty similar to this. So if you want like more insight as to what you do with this stuff, um, so you can look at that. So here's just some final tips. Seems like most of you guys are distracted anyway. Um, bring your calculator. One of my friends definitely sold on that. Ended up getting it too. Write down all your knowns. Um, if you get stuck, you know, write down everything you know as well as relevant equations. Uh, and good luck. It seems like a lot of you guys in chat, especially Sreethan. If you don't get a 5, dude, you're actually selling. Um, and get enough sleep the night before, obviously. So here's my contact info. I do tutoring for this class, the other AP Physics. I do Calc, AB and BC, Bio, Chem, and what else? Oh, SAT. That's right. I got into Carnegie. I just didn't end up going because I live near here. So I was like, why would I not just go to UT? All right. If no one has any like questions or anything, uh, wait, what was? Okay. Thank you, man. What extracurriculars? I had a I had like 70 hours like hospital volunteering. Our whole like cohort's extracurriculars were terrible because of COVID. That hit when I was in sophomore year. So like all of that were like really bad. Stats looking like to get into CMU. Um, thank you, man. What did I have? I had a 1560 SAT. I had like fives on most of the STEM APs. Uh, what else? I had the hospital volunteering. I had a pretty decent essay off of that because I was able to write about the time I was like, I held this lady's stomach after the procedure. So that was super dope. And I talked about how that like inspired me to want to do medicine. Some steps for any MC. A lot of times you'll just get it initially. So obviously you don't need help on those. But definitely write out your knowns, draw out any free body diagrams you can. Uh, and then just look at the relevant equations. Those will help you guide through it, or it'll help guide you through it. were you saying? The application for CMU. I think I did it through Common App, so it was like the same as everything else. It wasn't anything crazy. Is it worth majoring in physics? I want to be. Well, if you want to be a theoretical physicist, I mean, like, how else would you do it? I don't know. That's definitely the way to go. There are career options. Obviously, it's going to be a little bit harder to step out of that sphere eventually. But if you're set on that, you're set on that. No problem. Thanks to everyone who showed up. Thanks for staying the whole time. I really appreciate it. And good luck on the test. Um, what do you mean the ones they offer? I don't know what you're talking about. But also remember, if you have a decent grasp on it, you only need like 50. You need like a 50 to get a 3, something like that. All right, well, thanks to everyone who stayed to the end. I really appreciate you. A neuroscience would benefit an AI major. I have no idea what that means. Sure. I'm minoring in comp sci, so I guess there's like an overlap. I don't know, but we'll have to see. Okay. The ones on AP Classroom. Yeah, those are about equal difficulty. Yeah. Those are equal difficulty. I don't know what you mean by an AI major. Usually there's like AI programs for masters, but for undergrad, I think it's just like comp sci. Sorry I'm answering these questions so late. The delay is super crazy. And if you guys ever want to contact me, just go ahead and like DM me on Instagram, email me, whatever. I'll get back to you as soon as I can. Um, Again, thanks for sticking to the end. I'm gonna go ahead and end it here if I can find out how to end it. You too.